second and last talk today by a local, it's Eduardo Esteves from IMPA, on polymatroidal tilings associated to limit linear series. Please.
Okay, thank Alicia. It's a pleasure to be here celebrating Fernando. So the subject of my talk is something that certainly Fernando was interested in the early days of his career. It was a subject of Joe Harris, and it influenced many people, not just his students like Fernando, but other people as well like me. I first met Fernando at a conference in UCLA, which was organized by Rob Lazarsfeld. So Fernando had moved already to Kansas, but came back to the conference. And the first thing that struck me when I met Fernando was his enthusiasm. And about math, about life, about the way he would speak to people. And I think this is corroborated by his students. And just, an hour ago by Angelo with his late night math. So thanks again for the invitation. It's a pleasure to be here. So I'm going to talk about this. Oh, yes, I was wanting to mention as well that in those days he was enthusiastic also about a set of notes that later became a book by Gelfand, Kapranov, and Zelevinsky. And if maybe I had paid more attention to his enthusiasm, this should have come a bit earlier. Because I'll make a connection between the two subjects. I mean, this limit linear series and the work by Kapranov. Okay, so let's start. So, brief history, the generations of linear series, it's a very useful tool for understanding curves, for understanding general curves, for understanding families of curves in the moduli. It was famously employed by Severi as an attempt to prove Brunner theorem that describes linear series on general curves. And the actual proof came later by Griffiths and Joe Harris, whose work was simplified and conceptualized by Eisenberg and Harris with their theory of limit linear series. Okay. So the approach that they had worked only for curves of compact type. I'll just explain what they are later. And they called for a more comprehensive approach in the late 1980s. And that comprehensive approach, working for every curve over the moduli, is not yet available. Okay. So linear series, of course, are spaces of sections of line bundles. So if you want to understand how they degenerate, and that's what the subject is, a limit linear series, we may try to understand how line bundles degenerate. And then there is work by several people. It started with de Souza in the 70s for a single curve, Ottman and Kleiman for families of curves, all of them irreducible. Oden Seixader extended to reducible curves, so in particular stable curves. And Caporazzo was able to do the construction over the moduli of stable curves of a compactification of variety of the Picard scheme. I did some work on families of reduced curves. There is work by Mello, Viviani, and the two Brazilians, let's say, Pacini and Abreu, using tropical methods. It's a very recent method. And then there is work also by Cassi and Pagani. I will mention that work, their work soon, actually. Okay? So that's to give an idea that, indeed, I mean, the subject has lots of people working, lots of results. So line bundles, how they degenerate, we sort of understand this. And there are two approaches. You can think of these degenerations of line bundles as line bundles on a semi-stable model of the curve. So you just split the branches apart and put chains of P1s. Or you can take the direct image and view them as torsion-free rank-bound sheaves on the curve itself. The two approaches are interchangeable. I will take the second. And what's a torsion-free rank 1 sheaf? Well, all of them can be described as subsheaves of line bundles where you have this ideal sheaf, and F is just any subscheme. So if it's a Cartier divisor, then you get a line bundle. If it's not, you get just a sheaf. Okay? So every torsion-free rank 1 sheaf, of course, we're talking about abstract sheaves, but so they can be realized like this in different ways, but still be the same sheaf. Okay? So in each case, either look at line bundles on the semi-stable model or torsion-free rank 1 sheaves. There are actually infinitely many limits of line bundles, infinitely many degenerations of line bundles, if your curve is reducible, if it has more than one component. So let's see an example that we're going to use for very simple one for the remaining of the talk, which is the case of the triangle. So simply given by the union of the coordinate axes in P2. So that's my curve C. And I'm going to look at a pencil of curves, a pencil of cubics, just pick F, a general cubic, degenerating to the triangle. So the curve F is somewhere around here. Of course, it's a cubic. It intersects in the 3 points. Yeah, something like that. It should intersect in 3 points each line, right? So that's the general cubic. And I'm considering that family of curves. And this series cut by the lines on P2. Okay? So as simple as that. If you pick a general line, of course, it will intersect the curve C in 3 points. So these are degenerations. But if you pick the line x equals to 0, it contains part of the curve. So what can we say about this? Well, if we look at the intersection on CT, then the intersection is just this set of points. Just plug x equal to 0 in the equation and t non-zero, then you get this intersection. And these are 3 points that don't move with t, and they're actually the limits. And they lie on one of the components. So you see that you have many different limit divisors in this situation. You have the 3 points on a line, there are limits of divisors, but 3 points on a single component they are as well, and they are not linearly equivalent. So it started with a system that generally, was of linearly equivalent divisors, but as the divisors degenerate, you don't get linearly equivalent ones. Okay? So the bottom line is then that both OC of 1 and OC of this D, there are limits of OCT of 1 as t goes to 0, because they are limits of equivalent divisors for t non-zero. Okay? So there are many limits. I just showed you 2, but actually there are infinitely many. So how do we what do we do, right? So that's the question. And then stability conditions were introduced so that we could pick up the limit that was right for us, maybe. Okay? So let me talk about these stability conditions. So let's assume from now on that C is nodal, projective and connected. I'll let V be the set of irreducible components of C. And in order to use small letters, V in V will correspond to the component CV. Right? So I'm actually picking a set in bijection with the irreducible components. I'll do the same thing for the nodes. And I'm using this notation because we have a graph with vertex set V and edge set E, which is called the dual graph of the curve. It's dual because the dimensions are reversed. So if you have, so what's the relation? E is an edge connecting U and V if and only if the corresponding node lies in the intersection of the two components. If it lies in just one component, it's a self-node, then you have a loop in the graph. So in the case of the triangle, the dual graph is a triangle. But things get reversed. Okay? So I will introduce then the stability conditions. I need to define this C of S. So for every subset, I look at this subcurve, which is the union of the corresponding components. And given a sheaf, a torsion-free sheaf like that, I will define a function on the power set of V, on the set of subsets of V, where I associate to every S this sum of the degrees minus the points of intersection with F. In fact, you can read that as what is the degree of our sheaf L on C of S. If L was an invertible sheaf, a line bundle, that would be the degree. But then there's this correction term that doesn't depend on L at all. It's just the points of intersection of this subcurve with the complementary subcurve and divided by 2. Okay? So let's keep that. I put on the board. Also, for every R-value function on V, right? So we can define Q also on the subsets the same way. I am summing the values of Q on the vertices, right? This can be thought of maybe a real valued multi-degree on your curve, because this V corresponds to the components of the curve. And then this is the definition of semi-stability. It depends on the choice of this Q, which we call a polarization. And the condition is that Q is everywhere bounded above by mu of L with equality for the whole set. Now, if you have seen references before and you're going to look at the references in the papers that are out there, this appears a lot. This is the basic inequality by Caporazzo, but it's not usually put in that way. So it's usually put with focus on the degree. So basically that's saying that the degree of L on C of S is bounded below by Q of S minus this term here. And also because I'm putting equality there, that means that you have an inequality on the other side as well. So the usual way to put that is that the degree of this on C of S minus Q of S is bounded above in absolute value by this. So you're not going to find it this way, and I'll explain later why I'm putting this way. It's connected to what we're doing. Okay? So these are conditions of stability, is a way of choosing sheaves with a particular choice of this value Q. Okay? So in our example, OC of 1, and I'm using this notation there, so Q is the constant function 1, it's going to be 1, 1, 1 semi-stable because that's the multi-degree of the line bundle, but it's not 3, 0, 0 stable. It's too far from 3, 0, 0. Whereas that other line bundle, which was concentrated on one of the components, has actual multi-degree 3, 0, 0, so it's 3, 0, 0 semi-stable, actually stable, but not 1, 1, 1 semi-stable. So stability allows you to choose which line bundles you want to consider and to try to construct a moduli space. Right? But if you were to construct a moduli space of these sheaves over the moduli space of stable curves, there is one thing that we must make sure, that we need to choose these values of Q, one for each stable curve. And they are very different dual graphs, the stable curves. And we want to make sure that if we have a family of line bundles over a family of curves, if a single sheaf is semi-stable, the nearby sheaves are as well. So semi-stability should be an open condition. But you let this Q vary wildly, that won't happen. Right? So the question is there a natural stability condition? Is there natural choices of Q that work on families over the moduli? Right? And the answer is that there are. There is Caporazzo's canonical polarization. So you just take the canonical bundle, the dualizing bundle, and look at its degree, its multi-degree, right? And you scale it so that the value of Q over the whole set is D, right? So that way you can define semi-stability for degree D line bundles, right? There is of course, I mean, the denominator must be non-zero, so that works for G greater or equal than 2, which is not the case of my triangle, but okay, let's keep at that. It's a simple example. I don't want to be more complicated than this. Right? I'll talk about what happens in the triangle in a moment. So that's how Caporazzo constructed her compactification over the moduli stable curves, picking that as a polarization. So, as I've just said, this works over mg bar and only this. Right? It's not surprising because we sort of know how many line bundles a general curve might have. So there's no other choice of possible stability conditions. That's what Caspagani proved. And that doesn't leave us much space, of course, which is very bad. So why it's only this? And one of the reasons is the symmetry of things somehow. So for example, in this example, we can consider this family of triangles, right? So the first factor, there are three factors here. The first factor for t equals to 0 is x, but for t equals to 1 is y. So if we assign a degree for the first factor, it must be the same on x and y. You're going back to the triangle. So you have families like this. And then, I mean, if you want to put a stability condition of 3, 0, 0, it won't work because it has to satisfy the symmetry. Right? So 1, 1, 1 is a good stability condition to work on families of triangles, but 3, 0, 0 is not. Right? Okay. But okay, if we can't naturally pick this 3, 0, 0, we cannot naturally consider these divisors, this degree. So if you're just restricted to looking at that limit, the limit of the line section series, how do we explain that divisor there? So if we pick a general line, and make this line degenerate to x equals to 0, what you're going to see is that in the limit, the nodes will appear. So you won't get this divisor here. So how do we explain that? And another interesting thing, how do we explain the flexes? So every smooth cubic has 9 flexes. So it's a set of points where the curve flexes a bit. Where do they go in the degeneration? So the triangle looks very much inflexible. It sort of breaks at some points, okay? But the spoiler is these breaking points are not limits of the flexes. But which of them are, in fact? Okay, so the approach by Eisenbud and Harris, actually, which was in the 80s, they didn't propose to consider stability conditions. In fact, they proposed to consider one limit for every component of C. So there are many limit line bundles, infinitely many, as I said, and they figured out that for each component, one of the limits would give more information, more relevant information than the others. That worked well for curves of compact type because they're compact type because the generalized Jacobian is compact. That's the name. So when you consider degenerations, you always have a limit line bundle. And you can always choose its degree, whatever multi-degree you want. And of course, they chose the multi-degrees to be 0 on all components but 1, the one they're focusing on, for each component. So that you cannot do for any curve. Right? So here, I was just looking at the sections, 1, 1, 1, I have 3, 0, 0, I have the other ones, but there is no limit which has degree 2, 1, 0. There is no such limit. Right? So you cannot have all assigned degrees in the general case. And if in the general case, what degrees should we assign? We don't know. Okay? So how to do it more generally? So that's the question that they left us to work on. There was some progress or a different point of view given by Osserman, who actually observed that the Eisenbutton-Harris approach was not really very functorial. So they actually didn't really define it over the moduli space, but they had some useful construction anyway. What he proposed was to consider all limit line bundles of effective multi-degree, right? So degree positive on every component, or at least non-negative, along a one-parameter family of smooth curves, degenerating, and in that case, it was a toy case, let's say, a unionodal curve of compact type is just a union of two smooth components meeting at a point. So it's a very special curve in a sense, but it was basically to illustrate the approach in a sense. So later on, he tried to consider more general curves, 2019, but it was a lot messier to deal with them, and even for one-parameter families, and we actually want to consider different bases, like the moduli space. Okay? So there was recent work by myself and two ex-students of IMPA, Renan Santos and Eduardo Vital. We used quiver representations to organize the degenerating data for one-parameter families. So I think it's a good work. I'm not going to talk about that. I talked about this a few years back. It's beautiful in its own, but again, it's for one-parameter families and for special one-parameter families. I'm going to talk about how special indeed. So we need an old idea, or we need a new idea, but we found an old one with a new application, maybe, right? So Omid and I stumbled upon work by Kapranov. So basically, we sort of realized at some point that what we were doing was, in a sense, generalizing something that Kapranov had done. So I will stop a bit about this linear series, and I will talk a bit about Kapranov's work. So in a very influential paper, he did the following. He considered a finite collection of finite dimensional vector space, and the action by the torus, so GM of V, that means that it's one copy of GM for every element of this set, V, right? And you have an action of this on the Grassmannian of R+1 dimensional subspaces of U. U is the sum. So basically, you take the subspace, you have an automorphism induced by GM of V on the sum, acting by a constant on each summand, right? And then you have this action. It's a torus action on the Grassmannian. For a general W in G, we expect the projection to be of maximal rank, which means it's injective or surjective.
Sorry, what is R?
Sorry?
You say Grass.
R+1 is the dimension of the subspace. Okay? Why R+1? Because I will connect this to linear series. Right? So R+1 is the dimension of the subspace that we are parametrizing of this large space U. Okay? So for a general W, these projections have maximal rank. We know what the rank is. It's just the dimension of W or the dimension of this U of S. So this S is just a subset. I forgot to put it here. For every subset of this V, you pick the sum, the partial sum, and you project onto the partial sum. And then what he did was to consider the closure of the set of orbit closures of this W inside the Chow variety. So let's go in steps. You have your W. No, it's here, sorry. Yeah, you have your W. You look at the orbit, which is this multiplication here. It's a locally closed subset. You take the closure. So I have a subscheme of the Grassmannian. You take the point corresponding to it in the Chow variety. It's a prime cycle. You do it for every W which has maximal rank, or general W, and you take the closure. So that's the construction that they did, and they call it, Kapranov called it the Chow quotient. So basically what we're trying to do, what he's trying to do is consider the action of the torus on the Grassmannian and to construct a quotient by this action. Right? So if you look at the prime cycles, basically what you're saying is that you're looking at the set of orbits. But as you take the closure, you get some points, different points on the boundary. Right? So I have to say that this was not exactly what Kapranov did. In fact, Kapranov worked with a more restricted setup where this U of V, the spaces had dimension 1. So he was looking at the maximal torus acting on the Grassmannian. Okay? But, so that's what I mentioned. He considered just that. But there were many works after. So soon after, Laforgue considered a setup which is useful for us, which is that the dimension of these summands are always R plus 1, which is the dimension of the subspaces we are considering. So the projections in this case, at least to a single summand, would be isomorphisms. So basically talking about a sort of compactification of PGL R plus 1. So that's Laforgue. And the general setup that I put to you now, it was done by Gian Siracusa, Noah, and Wu in 2022. So that's the setup. So all of them, I mean, they describe the boundary cycles as Kapranov did. So the boundary cycles, so things that lie in the boundary of that closure, they are sums, they are reduced cycles. That means the multiplicities are 1, and there are sums of orbit closures, right? Where these WY, they satisfy the condition that the associated polytopes, they form a polyhedral decomposition of the polytope associated to a general W. So now it comes the polytopes into the picture. These polytopes, they actually arose in 2 steps. They first associated a matroid in the case of Kapranov. In the case of Gian Siracusa and Wu, it's a generalization of a matroid. It's a matroid on multi-sets, right? And then the polytope associated to that matroid as a certain convex hull, okay? So paraphrasing Joe Harris, if you think that you're going to finally be explained what a matroid is, think again. I'm not going to explain that. So that's a famous sentence in the book by Harris and Morrison about stacks. Of course, matroids are more simple than stacks, right? The interesting thing about matroids is that they have several different definitions. And some of them are equivalent, some of them are generalizations, so they're not equivalent. So it's sometimes not easy to understand what a matroid is, but I'm not going to do it because what happened is that we proceeded directly to find these polytopes. So what are these polytopes associated to W? So as I said, Kapranov described them as certain convex hull. You pick some points and take the convex hull. We're going to describe them by inequalities. So to each W, we consider this mu of W, which is a function on the power set of V, to each set S, associate the dimension of the projection. Of course, if W is general, we know what the dimension is. But for different W's, we can have different dimensions, different mu of W. And then that's the polytope associated to W. It's the set of Q in this RV. In fact, they belong to a hyperplane because Q of V is equal to mu of W of V, which is the dimension of W in this case. It's R plus 1. Right? It's the projection to the whole space is the same as the identity. And Q should be bounded above by this mu of W. Again, this defines actually a polytope because the quality implies that there are some lower bounds as well. Okay? So you see that this is the polytopes that Kapranov considered. So if you go back to the statement I said before, so let's go back just a bit. So these are exactly this P of Wi, and the idea is that this P of Wi will form some polyhedral decomposition of the polyhedron associated to the general W, which is fixed. Because the function mu of W is fixed for a general W. Okay? So you're going to see lots of pictures of these polyhedral decompositions, but let's first say that we have some striking resemblance to the notion of stability the way I just defined a few minutes ago. In fact, we can look back and see that the semi-stability condition actually defines a polytope, the semi-stability polytope of L, which is the set of Q's such that L is Q semi-stable, and you see they satisfy the same condition in a sense. Okay? How this works, in fact, what do they have in common? What mu of W and mu of L, and then the polytopes they have in common. So there is this function mu on the power set, and these polytopes, they are base polytopes of polymatroids. I'll say something about that associated to submodular function. So a function is submodular if it satisfies this inequality for every pair of sets, S1 and S2. Right? So you can see that mu L and mu W are submodular. Mu W is submodular, it's just linear algebra. Mu L, it's very simple. This function here is not submodular, but if you add the correction term, it is. So that's why I added the correction term. So both of them are submodular. And if you have a submodular function, you can consider the associated polytope. And this is called the base polytope of the polymatroid associated to mu. So the polymatroid, you don't have the quality, right? But then you have something which is just bounded from above. It's not a polytope. And then you take the base, sort of. I mean, you look at where Q attains the maximal value for V, and that's called the base polytope of the polymatroid. So it's called polymatroid because one way of seeing a matroid is as a polytope, and this is a generalization of a polytope associated to a matroid. That's why the name, which I don't like, but that's the name that it is. And a lot is known about them. In fact, they appear a lot in combinatorial optimization. So there is essentially a Bible by Shriver on all of these things, and there's a whole chapter about them. So we know a lot about them. We know what their faces are, what the vertices are. We know a lot, actually, about them, which is good. So what's our theorem? It's the following. We consider now a smoothing of a nodal projective curve, C, with the dual graph, as I said before. And let's suppose that we have a linear series of degree D and rank R, so the spaces have dimension R+1, that is degenerating along a family of curves, that smoothing that I put there. And then you have several linear series which are limits of these linear series on the general fiber or on base extension of the general fiber, doesn't matter. And we're going to associate polytopes to them. We know already the semi-stability polytopes for Li. This Wi is a subspace of the sections of Li, and we can view that in that sum of spaces. So we can consider also the polytope of Wi inside that sum, right? Which is the polytope of the vector space. And alpha and beta, positive numbers, and that's the theorem. So the polytopes associate to the mu of Li. Let me read that part first. They form a polyhedral decomposition of the hyperplane of RV given by that total value equals to D. if you take the linear series, if you take the submodular functions associated to both of them, and you do this linear combination, you still have a submodular function for every alpha and beta. And you can consider also what happens, and what happens is also polyhedral decomposition of a different hyperplane. If you look at just the subspaces, they form a polyhedral decomposition of this simplex associated to the general W, which is in this case is the simplex here of all things which are non-negative. So Q is greater or equal than 0, all values greater or equal than 0, and the total value is this R plus 1. Okay? So let's look at pictures now. We have several pictures of them. So all the pictures are going to be related to the triangle. Why? Because it has 3 components. So you're looking to RV. RV is R3. We don't draw R3, but since they live in a hyperplane, we can project that hyperplane to the first 2 components. And that's what we get for the polytopes associated to the sheaves. So in the degeneration that we're considering here, the sheaves are going to be line bundles. So the polytope associated to a line bundle is always the same in this case. It's the hexagon. You can say a lot about the sheaves just looking at the polytope. The width of this hexagon basically will tell you how many points your sheaf is invertible and how many are not. Right? So that's one picture. That's a very boring picture, let's say, because our situation is very simple. But it can get more complicated. So in this case, I'm picking a smoothie such that the total space is not smooth. So when that happens, it means that the nodes of the special fiber, they have some AN singularity, and this N is the singularity degree. It's the L that you see there. And in the case, there are 3 points. There are 3 nodes, and I'm picking singularity degrees 2, 3, and 5. So it's just a different family, it's a different approach, but you get this sort of picture there. So you see that you have polytopes of different shapes. The hexagons correspond to invertible sheaves, and then you have the parallelograms that correspond to sheaves that fail to be invertible at a single point. They are still simple sheaves. The endomorphisms of them are just multiplication by constants. What you might not be seeing, but you should see, is that there are polytopes of not maximal dimension. So if you look at the lines and the vertices, they're also polytopes of sheaves that occur as limits. Right? But these sheaves are not simple. They decompose as sums of sheaves on different subcurves. Right? It can get more general. So that's a picture where one of the singularity degrees is transcendent. It's not rational. So that doesn't happen algebraically, but it happens analytically. And we can tell something about that as well. So what happens in this case is that the picture is only periodic when the ratio R is rational. So the singularity degrees are there. It's 4, 2 pi, and 11. And 11 over 4 is rational. So if you pick a polytope, the hexagon on the top, and you go down crossing the horizontal wall, and you keep tracking just crossing the horizontal wall, you're going to go back to the hexagon, and then you're going to repeat itself. So you see that there are 3 types of edges there, right? There is a vertical, horizontal, and a diagonal. And if you go across the diagonal edge here, the diagonal wall from the center polytope, you're not going to repeat itself never, right? Which was not the case before, right? If you go through the diagonal there, you're going to see that you're going to get to the hexagon, and then you're going to repeat itself. Right? So the fun is really when you look at these polytope decompositions, and you can say a lot about them. So as I said, in general, your polytope, we're going to have maximal dimension if your sheaf is simple. That's the case for line bundles, but also for other kinds of sheaves that will give you different polytopes. If you have a sheaf, so this is not just for limits, of course. Every sheaf has a polytope. if you have two sheaves which are simple and their polytopes share a wall, then they share some property. If there are maps between them, these maps are unique. Modulo multiplication by constant. And when you have a degeneration, these maps exist. So there are maps between the sheaves that are arising from the degeneration. These maps are not unique if the sheaves don't share a wall, but if they do, it's unique. Okay. So the picture you saw. Now let's talk about the vector spaces. And in the particular problem that we are considering here, we have these are the polytopes associated with vector spaces. So 1, 1, 1 is the system of lines on our curve. It has a large polytope. But then there are maximal dimensional polytopes associated to these multi-degrees there. Again, the lines and the vertices are also associated to the vector spaces, but these are vector spaces that we can obtain from the others. So I don't care much about them. So this is the picture of the associated decomposition on the vector spaces, just P of W. I didn't do the full example in that case because we had this picture from the paper. So the same pencil of curves that we took, but now instead of the net of lines, we picked a certain pencil of conics, just to give you a different picture that varies with the deformation. And here you see that you have a pencil of conics, so you have the pencil of conics on C, which has multi-degree 2, 2, 2. And you see that each of these polytopes there is associated to a certain degeneration, to a certain multi-degree. All of them appear. And if you put them together, there's those alpha and beta that we put the two polytopes together. What you get is a picture like this. The colors is just that we can differentiate between things. So it's an interesting picture that combines the pictures of the two cases, right? You might argue that these depend on alpha and beta, and it does depend. So these alpha and beta are similar to the stability conditions that people put on coherent systems, right? But if you put all of them together, as I'm doing, the picture is basically the same. So basically, if you change an alpha and beta, then some of these edges are going to be bigger, some are going to be small, but the total skeleton is the same. So if two polytopes have a wall in common for a given alpha and beta, they will have for every alpha and beta. That doesn't change. Okay? So these are the pictures. So I tried to convey that it's not difficult to describe this limit data or the sheaves or the line bundles if you know well what your degeneration is, as the case of the pencil of cubics, right? If you know what the degeneration data are, and it's somewhat harder, but it's possible also to describe things if you know what your degeneration data are not, right? So what I'm going to do now, I'm not going to prove the theorem. I mean, it's based on the analysis of the deformation. So basically, we're tabulating the data somehow. But what I'm going to tell you is what are we doing now. Right? So a bit of a teaser from what we're doing now. So Omid and I are able to describe this, the limit data of the degenerating canonical series when we know what our curve is not. So if the points are in general position and the direction of the degeneration to the semi-stable model is general, so we can fix the singularity degrees. And for each singularity degree, you go to the semi-stable curve and you pick a general deformation. Then we are able to describe all the limit canonical series. So it's actually possible to describe all these linear series in a sense. And the polyhedral decomposition helps us in describing everything. So that's the first teaser. Then there is a question about moduli. So we're also constructing a compactification of mg bar of this variety of relative linear series using these data as objects. You might think that how can we manage it if there is only one natural polarization, which is the canonical over the moduli? How are we able to consider all these other shapes then? Well, the thing is that there is a strength in numbers. So that's just a joke. But the fact is that whereas the polarization 3, 0, 0 cannot be assigned to the triangle, because what you think was x would become y and these sort of things, for the symmetry reasons I outlined, the collection of polarization can be assigned. So if you track what happens along your family, your 3, 0, 0 becomes 0, 3, 0, but 0, 3, 0 becomes 0, 0, 3. So the collection is the same. And what we need is to give you a collection of line bundles that are semi-stable with respect to this collection, to all of the collection. So that's the idea. To finish, one more teaser is about maps. So linear series, of course, important because they describe maps. In the case of actual linear series to projective spaces. But in this case of this linear series, we can also have maps to a different object. So what we can do is we can consider the quiver associated to the polytope decomposition and its representation by linear series. So let's go back to go back here. So let's go back to the picture here. So that's the picture that I want. So to every polytope, I have a linear series, right? So every polytope is going to be a vertex of my quiver. Every wall between two polytopes, I'll put an arrow going forth and back. Right? And so to each polytope, to each vertex of the quiver, I have a linear series. And if the two polytopes share a wall, and I know there is a map between them, that map is unique. And I use that map to give you a map between the linear series. So to each arrow, I have a map between the linear series, which is a map between the sheaves that take vector space to the other. Right? So that's how we constructed this quiver representation associated to the polytope decomposition. So L is a representation of that quiver on line bundles. So I'm taking just the sheaves, right, or the sheaves. And W is the representation by vector spaces of sections of these sheaves. I can use, as usual, the evaluation maps for each of these sheaves and look at the spaces. And what I get is, for a general point, a one-dimensional representation, sub-representation of the dual representation. I have to dualize to go to one-dimensional sub-representations, right? So we get a rational map to the quiver Grassmannian associated to that quiver representation. So LPW star is the associated quiver Grassmannian. We call this a linked projective space because it's a quiver Grassmannian of one-dimensional sub-representations. Can we describe this? Yes. So let's look at our example to the triangle. Let's describe the map and describe this space. So what is this map? In the case of the pencil and in the case of the degenerating linear series cut out by lines. So here's the picture. You have on the base, it's P2. The triangle is there in yellow. You have these three surfaces, sort of vertical surfaces. They are Hirzebruch surfaces. So you blow up a point, and you get the exceptional divisor, and use that exceptional divisor to attach, to connect, to identify with the line on the triangle. You do that for each of these Hirzebruch surfaces. And the curve is actually, the map is well defined in this case, and the curve is there. It's actually on the Hirzebruch surfaces. It just touches the base P2 on the vertices. And you see now that it sort of twists now. So little did we know that the humble triangle was just a shadow of what is really happening with the degeneration data, which is what's happening above. So if you project down along the leaves of those foliations, yes, I managed to do that, to say foliation, but it's just a vibration, of course. You get the triangle. So thank you.
Beautiful picture to end. So why do you don't get rational? You get in general, you don't get rational slopes.
Right. Yes.
Why?
Right. I didn't say much about the method. We use tropicalization. There are tropical methods. So we actually look at the associated metric graph, and we just look at any edge length, basically. So we have a way of describing that. Yeah.
Good. Any more questions for Eduardo? Yes.
Very nice. It's good to see that the correct combinatorial approach seems to be this or some. Yeah, very nice. And you said foliations, and actually, I think we talked about this some years ago.
Right, we did.
Limit foliations, right?
Yeah.
So is it? So the idea would be to do, instead of curves, doing reducible projective space, union of projective spaces that intersect in some controlled way, and replacing line bundles by bundles, vector bundles, or foliations, or stuff like that. So, do you think this is with this new combinatorial approach could be possible to advance on this? Because it looks very complicated, but maybe having the right combinatorics could be something doable. I don't know. What do you think?
Right. As I said, it looks complicated, but it's not, because I have a very good control of what's happening, and the combinatorics is actually helping us to see everything, right? If we had the right organization. So I think that, yes, I mean, it's possible that you can generalize these to higher dimensions, so the generation to linear series on higher dimensional varieties, or foliations, right? We're not pursuing that. I mean, we're pursuing the things that we're doing right now. I mean, I talked about the construction of the moduli space and everything. But it does look very approachable. I mentioned this quiver representation, and in the paper with Renan and Eduardo, we actually do that for higher dimensional varieties. So the generation of higher dimensional varieties with total regular space. Then we get a quiver representation out of that, of the linear series, and we get this picture, the same picture. So it's possible. If it's possible then, I think it would be possible also for these polymatroids.
Thank you.
Any other question? Okay, if not.
So I have
yes,
one more slide to show
please.
you. So an afternoon suggestion for you. Since we have the free afternoon, of course, you're free to do whatever. But a suggestion is to go to Urca, where the dinner will be. Take the Pista Cláudio Coutinho, then the trail to Morro da Urca. Watch the sunset, watch the city lights, then take the cable car down and go to the dinner because it's right there. So the cost of that, well, excluding the dinner, it's very reasonable, I think. So the details are these. The trail is to Morro da Urca and not to the Sugarloaf. Don't go fall off the cliffs, of course. I mean, be careful. It's the first stage of the cable car, not the last stage. Take a lamp. The sun sets at 5:15. Don't start after 4:15, right? It could be your phone. If it's well charged, it will work. Right? And the trail is closed, actually, when it gets dark. When it gets dark, it gets really dark. I mean, I wouldn't be able to see this man here, right, at this distance when it gets dark. It's really dark in the trail. So you don't want to get to be there when it's dark. And the trail is actually closed when it gets dark, and that's why you can take the cable car for free, because you have to get down somehow, right? So bring a jacket. It can be cold. You're exposed there to the wind. And we can go together if you want. We can meet at 3 p.m. at the entrance hall, or 4 p.m. at the start of the Pista Cláudio Coutinho. Google there. You're going to find that in the map, right? And whatever you do, just enjoy. Okay. There's one more question here. Oh, maybe you can take a picture there, or it will be easier, or no. Yeah. I'll leave it there. Yeah. Maybe it's easier.
Yes, take a picture.
Maybe it's faster also.
Okay, we meet either there or just for dinner.
It's
and
at
then
7 o'clock, right?
7 o'clock at
7
Terra
o'clock.
Brasilis. And then we reconvene tomorrow morning for the lectures.